All right, so we are all in this race to build bigger, smarter AI, right? But here's the thing. We're hitting some serious walls. And I'm not talking about software bugs. I mean physical walls. Walls of performance, walls of power, and yeah, even the literal walls of the data center. So today, we're going to dive into the 3 hidden bottlenecks that are holding back AI's true potential and the amazing breakthroughs designed to just shatter them.
To really get what's going on, we have to completely shift how we think about this. You can't think of an AI system as just a rack of servers anymore. No way. You have to picture the entire data center as one single, massive computer. And if the data center is the computer, then the network, well, it isn't just a bunch of cables. It's the very fabric that defines how powerful that computer can actually be.
And this new kind of computer, we call it the AI factory. And let me tell you, its demands are completely fundamentally different from the traditional data centers that we're all used to.
I mean, just look at the difference here. A traditional cloud is handling millions of totally separate tasks. Your email, my video stream, someone else's web search. It's all about handling average traffic. But AI training? It's the total opposite. It is one enormous, tightly coupled job where thousands of GPUs have to talk to each other in perfect, synchronized bursts. The goal isn't just good enough or average, it has to be predictable, rock-solid performance every single time.
And this brings us to the main villain in our story, jitter. The best way to think about it is like an orchestra. Imagine if one violinist is just a tiny fraction of a second late. The entire performance just falls apart, right? Well, in an AI factory, jitter means thousands of incredibly expensive GPUs are just sitting there, idle, literally waiting for the slowest data packet to arrive. It absolutely murders performance, and it's a problem that old-school networks were never, ever designed to solve.
So this jitter problem, it creates our first major bottleneck, the performance wall. The challenge is building a network that can handle the unique, almost high-strung demands of AI. And the solution? Well, it starts by completely rethinking Ethernet from the ground up.
The solution is this end-to-end system called Spectrum-X. And the key thing to get here is that it's not just a faster switch. This is a whole system. It combines the switch with a new kind of network card called a SuperNIC. They actually work together. They talk to each other to intelligently manage traffic and avoid congestion before it even happens. This is how you get that perfectly synchronized, super low jitter communication that AI absolutely craves.
Okay, so what does all that fancy engineering get you in the real world? It gets you this number, 42%. Now that is not a small tweak. I mean, think about it, a 42% performance boost. That fundamentally changes the speed of research, of development, of innovation itself.
And that 42%, it's not some theoretical number from a perfect lab. Nope, it comes from training a massive model like Meta's Llama 3 in a busy, messy, real-world data center. In that kind of noisy environment, Spectrum-X trained the model 42% faster than standard Ethernet. It proves that it can cut through all that chaos and deliver that predictable performance we were talking about.
And the wins are just consistent right across the board. We're talking 35% better performance for core communication libraries, a massive 3x boost for those mixture of experts models, and way higher effective bandwidth. It's a system that's literally designed to hunt down and eliminate performance bottlenecks wherever they might be hiding.
But here's the thing. You solve the performance problem, and you immediately create another one. You smash right into the next wall, and this one is pure physics, power. The amount of electricity needed to run these AI factories it's just staggering, and frankly, it's unsustainable. To put this into perspective for you, in a 100,000 server AI factory, just the tiny optical transceivers, the little components that turn electrical signals into light for the fiber optic cables, they alone can consume 40 megawatts of power. That is enough to power a small town, just for the networking. This is the hardware bottleneck, and it is a huge one. The solution here required a pretty revolutionary shift in hardware design. See, we've always used these external, pluggable optics. They're bulky, they generate a ton of heat, and they are wildly inefficient. The new approach is called co-packaged silicon photonics, and it basically integrates the optics directly onto the switch chip itself. This one move radically reduces power consumption and massively increases reliability.
So, what is the ultimate payoff for this incredible piece of engineering? It's this. Approximately 3 times.
That 3x means you can run 3 times the number of GPUs within the exact same power budget. Think about that. All the power you were saving on networking can now be used for actual computation. This is a massive leap in AI density.
It lets you add incredible capability without needing to, build a new power plant to support it. It is a complete game changer.
Okay, so we've solved performance inside the data center. We've tackled the power crisis, but what happens when your AI model is so ridiculously massive it won't even fit in a single building? You've just hit the third and final bottleneck, the physical walls of the data center. So how do you build a computer that's bigger than the building it's in?
This is where the next evolution, Spectrum-XGS, comes into play. This technology is designed for one specific purpose: to smash that geographical bottleneck. It basically lashes multiple data centers together across an entire region, forcing them to act as one single, cohesive, giga-scale AI supercomputer.
Trying to connect data centers with off-the-shelf Ethernet is just inefficient. You suffer this huge performance penalty no matter the distance, and managing it is a nightmare of totally separate networks. Spectrum-XGS creates a single unified fabric. It's smart enough to automatically adjust for the distance between the sites, and its whole end-to-end architecture is designed to minimize that cross-site latency and jitter, which, as we know, is critical for these distributed AI jobs.
And the results are crystal clear. For an AI task running between two sites that are 10 kilometers apart, Spectrum-XGS delivers nearly double the performance. This is the kind of technology that makes building city-sized or even country-sized AI computers a practical reality. So, to bring it all together, we have these three key innovations, and they're all working in concert. First, you have Spectrum-X, which breaks the performance while inside the data center. Second, you have co-packaged silicon photonics, which breaks the power and hardware wall. And finally, you have Spectrum-XGS, which breaks the physical wall of the data center itself, allowing for almost limitless scale.
Each of these breakthroughs solves a critical problem, and when you put them together, they form a whole new foundation for the future of artificial intelligence. We are moving from computers that fit on a desk to computers that fill a building to AI supercomputers that can now truly span the entire globe. Which, of course, leaves us with one final, fascinating question to think about. When the physical limits of computing and geography are removed, when an AI computer can truly scale without limits, what are the grand challenges that we will finally be able to solve? Thanks for watching.